let's take a look through some word problems that involve rational equations. So this first scenario, we have a rare species of insect in the Amazon rainforest, and what they're doing is they're tracking the population of the colony T days after the transfer. So P is our population, T is the amount of time that's passed. So we want to find the y-intercept of P and interpret that value in context. So what that means is plugging in T equals 0. So we're looking at P equals 50 times 1 plus a 0.05 times 0, all over 2 plus 0.01 times 0. So that should be 50 divided by 2, which is 25. And what this tells us is when T is 0, what the population is. So the population is just 25. I was looking for units to add on if it was like 25,000, but it is 25 insects. And this is at the beginning of this new colony. So the population is 25 insects at the beginning of the transfer. So you transferred 25 insects in. Okay, after how many days will the insect population reach 100? So we're letting P equal 100 here. So we're going to have 100 equals 50 times 1 plus 0.05t over 2 plus 0.01t. So let's go ahead and multiply both sides by 2 plus 0.01t. On the left-hand side, let's distribute 100. So this will be 200 plus 1t equals, and on the other side, we'll have a nice cancellation occurring. So we'll just have 50. Let's go ahead and distribute the 50 in. So I'll go 50 plus 0.05 times 50, which is 2.5t. I'm going to subtract 50 from both sides and subtract t from both sides. So that'll be a 1.5t. Divide by 1.5, so 150 divided by 1.5 will be 100. So the population will be 100 after 100 days. There's a little work we can do there with a rational equation that's given to us. In this next example, we're going to form the rational equation. So we have a large mixing tank, and currently it has 100 gallons of water and 5 pounds of sugar. And just because I'm visual, I'm going to go ahead and draw the tank. So we have this tank of sugar water, and right now it has 100 gallons of water and 5 pounds of sugar. Okay, that's what we're starting with. Now we have a tap opens up, and we're going to be pouring water in. So water is going to be flowing in at a rate of 10 gallons per minute. And then at the same time, sugar is being poured in at a rate of 1 pound per minute. What we want to do is find the ratio of sugar to water. So taking the amount of sugar and dividing by the amount of water in pounds per gallon in the tank, and we want to look at this after 12 minutes. So first off, let's just talk about what's happening separately. So for water, we're starting with 100 gallons, and then we're adding on 10 gallons per minute. So let's let T equal the amount of time that's passed. We're going to add on 10 gallons per minute that has passed. So after 1 minute, we have 110, after 2 minutes, 120, so on and so forth. Then for sugar, we're starting with 5 pounds, and then we're adding on 1 pound per minute. So after 1 minute, we'd have 6 pounds, 2 minutes, 7 pounds, 5 minutes, 10 pounds, so on and so forth. So if I want the ratio of sugar to water, what I'm doing is taking 5 plus t divided by 100 plus 10t. So if we want to see what's happening after 12 minutes, I'm going 5 plus 12 over 100 plus 10 times 12. And with that, let's go ahead and get a value out. So let's see, that'll be 5 plus 12 in the numerator over 100 plus 10 times 12 in the denominator for 17 to 220, but let's get a decimal. So that is a 0.077 for the ratio. So sugar to water, 0.077. Is that a greater ratio of sugar to water in pounds per gallon than at the beginning? Well, at the beginning, we had 5 pounds to 100 gallons. So let's see, as a decimal, with that, it was 0.05. And if it helps, you could think of it as like 5% of the mixture was sugar, and then now 7.7% of the mixture is sugar. So in terms of a ratio of, we're looking for which is greater, where we ended up at 12 minutes is a greater ratio than where we started. So we're adding in, not ration, ratio in comparison because of the larger value. Okay, this next one we have Francine is planning a 60-mile training flight through the desert on her cycleplane, which is a pedal-driven aircraft. If there's no wind, she can go at a rate of 15 miles per hour, and she's going a distance of 60 miles, and the flight takes 4 hours. If there is a headwind of X miles per hour, so let's talk about how this changes our distance, rate, and time. It will take Francine longer to fly 60 miles. So our distance doesn't change, that's still 60 miles, but it's going to take a different amount of time. So we don't know what time is. And then the rate, if it's a headwind, it's slowing us down. So what we would do is we'd have our regular 15 miles per hour, but take away whatever that headwind is. So if it was a 1 mile per hour wind, that's slowing us down by 1 mile per hour, so we would be going 14 miles per hour. So express the time it will take to complete the flight as an equation of X. So what we're going to do is express this in terms of time. So if distance is equal to rate times time, that means time is going to be equal to distance divided by rate. So for us, time is equal to 60 divided by 15 minus X. Graph the equation and explain what it tells you about the time Francine should allot for the flight. So we're going to graph 60 divided by 15 minus X. And let's take a look at what this shows us. So we can see is there's a vertical asymptote that's happening at 15. And what we're seeing is as we're close to 15, the time it takes, which is our output, grows a lot. So if we have a headwind of 0, we're seeing it would take us the 4 hours. So that was the first piece of information we had, was with no headwind, that journey would take 4 hours. Then from there, the amount of time increases, and it's increasing as the headwind increases. So depending on how strong the headwind is, we need to allot more time. And as that headwind gets closer and closer to 15 miles per hour, like just think about if it was at 15 miles per hour, we wouldn't be able to move. The plane couldn't move at all. So with that, in order to be moving, we have to be having a headwind of less than 15 miles per hour. And from there, it takes longer and longer. So graph the equation, explain what it tells you about the time Francine should allot for the flight. Allot more time for stronger headwinds. And those headwinds, the time gets bigger and bigger as we get closer and closer to headwinds of 15 miles per hour. Okay, one more distance, rate, time question here. So when estimating their travel time, pilots must take into account the prevailing winds. A tailwind adds to the plane's ground speed, while a headwind, like we just talked about, decreases the ground speed. Sky High Airlines is setting up a shuttle service from Dallas to Phoenix, a distance of 800 miles. So let's put, just for a visual, Phoenix over here, Dallas over here, quick little compass of north, east, south, west. And we're going between these two locations, 800 miles. Express the time needed for a one-way trip as an equation of the speed of the plane. And we're going Dallas to Phoenix, so we're heading west. So the distance, rate, and time, we have 800 miles. We're going to have whatever the ground speed is, so let's call that just R. R equals ground speed. And we don't know how long it takes. That's what we're looking for here. So we're just going to have T for the amount of time for the trip. So like we did in the last example, D equals R times T. But if we want to solve for T, we would take D divided by R. So T is equal to 800 divided by R. Suppose there is a prevailing wind of 30 miles per hour blowing from the west. So we're going to add a wind from the west to the east of 30 miles per hour. Write expressions for the flying time from Dallas to Phoenix and from Phoenix to Dallas. So let's go Dallas to Phoenix, Phoenix to Dallas, and we're going to talk about distance, rate, and time for each of those trips. So the distance covered is going to be the same. If we're going Dallas to Phoenix, that's going to be a headwind. We're going against the wind. Whereas Phoenix to Dallas, where we're going west to east, we're going along with the wind. So with that, it'll be a tailwind. So whatever our usual rate is, if we're going into the wind, so having a headwind would take away 30 miles per hour. If it's a tailwind, it's pushing us along, so the rate that we usually go at, we're going to add 30 miles per hour. And then time is going to depend on which trip it is, so let's call this time 1, time 2. So time 1 is going to be equal to 800 over R minus 30, whereas time 2 will come from 800 divided by R plus 30. The one being the trip from Dallas to Phoenix and the other being from Phoenix to Dallas. Write an expression for the round-trip flying time excluding stops with a 30 mile per hour wind from the west as an equation of the plane's speed. Simplify your expression. So what we're doing is we're combining these together. We're going to go Dallas to Phoenix and then Phoenix to Dallas. So we're going to add T1 plus T2, which should be 800 over R minus 30 plus 800 over R plus 30. And we want to simplify this expression, so let's get a common denominator. So this one's missing R plus 30. And this one's missing R minus 30. So distributing through, we'll have 800R plus 24 with 3 zeros plus 800R minus 24 with 3 zeros all over R plus 30 times R minus 30. And let's see, those 800 R's will add together, so 1600 R. The 24,000 will cancel out, so it'll be dividing by, and then let's go ahead and multiply out, so that'll be R squared minus 900. And that would be our simplified expression for the total time for a round trip flight if we have that wind speed of 30 miles per hour going 800 miles between the two cities.